Let us study about effect of temperature on resistance. Before that, let's understand what is the effect of temperature on resistivity. To understand this, let us consider a conductor which contains a lot of free electrons. Let us apply a potential difference across this conductor with the help of a battery, because of which an electric field is set up in this direction. Let us call this as end A, this as end B, and we know that electrons will move from lower to higher potential. So at some temperature, the electrons will move randomly. So electrons will collide with other electrons, and because of which they move in random direction. After each collision, they'll have a random motion. Electrons will keep moving like this. Now suppose if temperature decreases, then what happens is the electrons will have a lesser collision. Because the electrons are moving faster, they have more energy, they'll move faster. The more faster electrons move, there is a more chance of collision. The electrons move slower, collision will decrease. So as temperature decreases, we can say the rate of collision of electrons will decrease. Now since the rate of collision of electrons will decrease, there will be less force of repulsion between electrons. Now consider electron here. If they're moving faster, they'll have more collision with them, and also there'll be repulsive force with them. But the electrons don't move faster, then the rate of collision will decrease, because of which the repulsive force between electrons will decrease. Now because of which their drift speed will increase. So drift speed of electrons will increase. But we know that drift speed is equal to mobility into E. Assuming here E to be constant, drift speed is proportional to mobility. Now this means that since drift speed is increasing, mu also will increase. But this mobility and resistivity are connected, and the relationship between them is rho is equal to 1 by n E into mu. So since mu increases and rho goes inversely as mobility, that is because for a given conductor n remains constant and remains constant, therefore rho is proportional to 1 by mu. Since here mu is increasing, rho would decrease. So if you summarize this, we can say that as temperature is decreasing, that's what we saw earlier, rho also will decrease for conductors, or vice versa. If temperature increases, rho also will increase. Now if we take a case where temperature tends to low value, now theoretically the lowest possible temperature is 0 Kelvin. So at 0 Kelvin, what happens is rho should tend to 0. This means if a given material is kept at 0 Kelvin, or if we are able to achieve a temperature of 0 Kelvin for a given conductor or material, then rho becomes 0. These kind of materials are called as superconductors, but it is very difficult to achieve this property. Now coming back to our case here, it is seen that there is a direct relationship between temperature and then resistivity. Mathematically, there is a form for them, and that form is rho is equal to rho naught into 1 plus alpha into delta T. Now here rho is resistivity at any temperature. Resistivity at any temperature, say T. Rho naught is resistivity at reference temperature, which is generally taken as at 0 degree Celsius. This alpha is a constant for given material. It is called as temperature coefficient of resistance, and delta T is the difference in temperature, which would be difference in temperature for these two cases. Now different materials will have different behavior. For example, the behavior of copper and iron may not be same. The behavior of say nichrome and some alloy may not be same. So to differentiate those materials, we want a parameter that's called as alpha. So alpha tells us how would the resistivity vary for a given material. Now here you can transpose this in form of resistance also, because we know that R is equal to rho L by A, and then for given conductor the change in length and area is not affected by temperature change, so R is proportional to rho. So we can rewrite this formula in terms of R and say R is equal to R naught into 1 plus alpha into delta T. We are neglecting the thermal expansion of material. This is what we get. R is equal to R naught into 1 plus alpha into delta T. Now again the same things hold here, where R is the resistance of a material at a given temperature. R naught is the resistance of a material at a standard or reference temperature, and alpha is called as temperature coefficient of resistance. So this is the form given here. To define what is this alpha itself, you can say that from here, if you read this, R is equal to R naught. Some books will write R naught, R suffix T. Some books will write R naught as R suffix T naught. It depends on the book. We will stick with what did earlier, which is R is equal to R naught 1 plus alpha into delta T. If you rewrite this, then you can say from here R is R naught plus R naught into alpha into delta T. If we bring R naught this side, then R minus R naught is equal to R naught into alpha into delta T. If you bring this alpha and R naught down, or if you bring delta T and R naught down, then R naught alpha is equal to R minus R naught by R naught into delta T. We need to write this in words. So you can say that temperature coefficient resistance is equal to change in resistance of a wire of resistance 1 ohm at 0 Celsius when temperature changes by 1 degree Celsius. Basically what we're doing here is making this R naught. So we take that material for which resistance is 1 ohm at 0 degree Celsius. So this becomes 1 ohm, and we find out what is the change in resistance if the change in temperature is 1 degree Celsius. So this is what is given mathematically by form here. So you can say temperature coefficient of resistance is equal to change in resistance of a wire of resistance 1 ohm at 0 degree Celsius when temperature changes by 1 degree Celsius. Keep in mind that the temperature change would be same in Celsius scale or in Kelvin scale also, because it is only temperature change, and dimensionally this would be per Kelvin, or its SI would be per degree Celsius, or it will be per Kelvin. Now let us look the behavior of the temperature dependence of resistivity of certain materials. There is a direct relationship between resistivity and then temperature for nichrome. That is because from the form what we saw earlier, rho is equal to rho naught into 1 plus alpha into delta T. This is a straight line. This is what we get from here. And then for copper, it has slightly different behavior. Let us not go into why this happens. Just learn from example point of view. And even here also, it's almost a constant and increases linearly. While what is interesting is a device called as semiconductors, it goes inversely. Again, there's no need to understand it for now. We'll do it in chapter on electronics. For now, keep in mind that for semiconductors, it goes inversely, which means if temperature increases, resistivity will decrease.